right, hello everyone, and welcome. My name is Nick Lotz. I am on the community team here at Voxel 51. Hopefully, folks can hear me okay as well as see my screen. Welcome to this webinar workshop. It is somewhat creatively named Debugging the Future. There's a reason we call that because the focus is going to be on action conditioned models. So this is going to be a computer vision video based workshop. Um, the goal of this workshop is to think about in the context of all the action conditioned video generation models coming out of companies like OpenAI, NVIDIA, DeepMind, and so forth. We need to realize that we're coming at constraints not necessarily just in the model layer, but especially in the data layer. These models are generating really plausibly good looking future video. It looks really good, but looking right and actually being right at a physical layer is not the same thing. So whether you're using these models for autonomous driving, for robotics, industrial applications, you're probably aware that these ultimately, when these models are generated in synthetic video is used in production, they need to actually map to what reality looks like. So the goal of this talk is to give you a practical playbook for validating world models. A little bit about myself. As I said before, my name is Nick. I'm on the community team here at Voxel 51. My background is into computer vision, kind of in a non-traditional route. I think many people are like that. My academic background is chemical engineering, specifically in silico simulation of primarily biological modeling. So I worked in clinical settings. My focus was largely on pulmonary systems, and I was kind of there for the transition from extremely deterministic models that were based off kind of the model predictive control principles and systems theories of 10 years ago, much more now into kind of the neural net and then now uh, deep learning models of today. So excited to walk through this talk. Couple things, just logistic things I want to talk through in a moment. First of all, as we go through the content, all the resources presented here will be sent your way in a follow-up email after this talk. So the slides, the Jupyter notebooks, I'll go through together. In addition, all the examples I do are, or I should say 99.9% of what I show is possible in the open source implementation of the 51 SDK. So the goal is to be able to reproduce what I'm showing here on your own laptop with, as long as there's sort of a minimal amount of ideally GPUs enabled on it. One last thing I want to do, and this is going to be a shameless promotion, not for myself, but for a colleague, is that there is a workshop tomorrow as well that is focused on MCP and skills. The link and QR code is on this slide. If that is something you're interested in, I highly recommend you attend. We are expecting a very big group, but since it's virtual, it'll be great if you're able to attend. There's definitely no constraint or capacity issues on that side. My colleague Adonai, also on the community team here at Voxel 51, will be leading it, and we'll also have speakers from Hugging Face and NVIDIA. And the context of all this is just the way tools like 51 are built. They are extremely SDK first and API forward, which makes them ideal for a Gentic style interaction or even or a Claude skill or any type of AI skill style development as well, and integration with MCP services. So again, if that's something you're interested in, highly recommend you sign up. It'll be tomorrow at 9 a.m. Pacific time. Cool. And I'll do a shout out at the end as well. All right. So here is the landscape for today. We're going to start with, all right, here's the agenda for today, starting with the landscape. We're going to start with what is happening in world models right now and why validation is such a hard problem. And then we'll talk about the data challenge. That is like, how do you even navigate tons and tons and tons of video to find the scenarios that you care about? And then finally, not finally, next we'll move to validation. Basically, we'll look at how do we actually check um, physics beyond the standard metrics that we might be familiar with. There's going to inevitably be a trial and error approach. So the goal is to align any type of like temporal interaction with any type of ground truth and both verify issues in the model we're training, the model we're trying to use to generate video, and then also like keep a skeptical eye on the ground truth data as well. Then we'll do what I call curating for causality. That is, how can we find those really rare high leverage scenarios that make models better. The idea is to be able to incrementally move forward our model's performance with as little compute costs and as little like, you know, needle in the haystack time as possible. And there's good techniques we have for doing that. And then we're going to have an interesting discussion about red teaming. That is, how can we use human expertise to catch what automated metrics might miss? All right. So I want to set the stage with a few numbers that kind of indicates how real and a big deal this is. So the company Runway last year raised a $3 billion valuation, and the company is built entirely around video generation. NVIDIA trained their Cosmos model on 20 million hours of video, and that's about 100 million clips. And then you have others like Sora from OpenAI, Genie from DeepMind. There's at least a dozen companies with really serious video generation capabilities, and they have serious money behind them. And this is based on the promise that you could potentially train a self-driving car entirely in simulation without driving a single mile. Like that's an incredible promise um, that we're kind of looking for. Um, and the term physical AI is all over the industry, right? NVIDIA is explicitly calling Cosmos a world foundation platform or a world foundation model platform for physical AI. The bet is that world models become the engine, the physics engine for robotics and autonomous vehicles. However, there's a big catch, and if you're in the computer vision space, you probably know this intuitively, is that a model can generate a car that looks really, really good from like a, human eye first pass and a scene that looks really good. And then that car drives like straight through a concrete barrier, right, without slowing down. So despite the visual quality that looks really good in demo, often the physics just isn't there. And that's where validation matters. We need to ensure physics fidelity. So that is where action condition models come in. So let's be really precise about what we're actually validating here. An action condition model takes two inputs. It takes the current observation. So let's say we have a frame or a few frames showing the world as it is right now. And then there's an action command like steer left, brake, if we're talking about, say, self-driving cars. And it runs those through a transformer or diffusion model and then produces our predicted frames, right? What is the um, predicted next step? So what's really important about these is if you're generating, say, the next 3 seconds of an autonomous driving scenario, it can't just look correct, right? Again, if the physics is not realistic, that's how people get killed ultimately, right? If there's not proper physical fidelity. So the prediction has to respect causal physics, right? For example, when you brake, the car has to slow down, it has to decelerate at the proper like deceleration rate. If there's a wall ahead, the car has to stop. So the pipeline we're looking at here is, frames plus action go into the model, and then a predicted future comes out, but the action input is like what changes everything, right? It's what makes world models useful for planning and for simulation. And it also makes the output testable, right? So if you specify the action and then, the video comes and then the frames come out, you can check whether the output is physically consistent. So that testability here is what we want to exploit. So what can we measure today? So there are quite a few metrics and mechanisms for validation. There's the Fréchet inception distance, so FID, which you may have learned in like computer vision grad classes or used today in your work that you do. And the idea is, does it tells us whether the generated distribution looks like the real one. And then FVD does a similar thing for video. We have measurements on perceptual similarity, and then clip scores show semantic alignment. So like they're all metrics that can be useful in and of themselves, but they all more answer the question, do they look real, right? It doesn't tell us whether the physics are actually right. So on the right here is a classic confusion matrix, right? That's a model getting confused between object classes, and maybe like cars and trucks are being confused, maybe like motorcycles and bicycles are getting confused. That same type of confusion happens with physical properties, right? So like a model that looks correct can ultimately be a total failure when it comes to how it's actually responding to gravity. So a good kind of paper that backs this up is on PhysGen Bench. That tests 27 physical laws across 160 prompts. And then the best model, which is Runway's Gen 3 model, scores 0.51, which is like halfway to perfect. And then some of the other major models from companies like Google DeepMind, they found that no video model exceeds 30% of real world physics understanding. Sora scores just around 10%. So it's been really tough to find a correlation between like visual realism and then actual physics understanding. So all of this background is to say that we need a different kind of validation. But before we can really talk about that, we need to understand the scale problem because data is a really big constraint here. Um, we need to find the right data to validate against. So NVIDIA's Cosmos model was trained on about 100 million video clips, extracted from 20 million hours of raw video. The new scenes data set, which is a common multimodal kind of benchmark self-driving data set, um, the ratio of the rarest cases to most common cases is 1 to 10,000. There's not a whole lot of like rare cases to test against that are likely to actually result in model failures, right? If everything is like, empty or mildly crowded roads on a sunny day, that doesn't represent the safety critical scenarios that we need to actually build and test for. Um, so this can be summarized in what's known as, or what's been coined, the curse of rarity. Um, the idea is that when rare instances are rare in the real world, it can be hard to capture them in real world data because, well, they're rare. And then, yes, yeah, that mentioned in chat as well. Isn't there the issue that the prediction of the future would only include the car, but the models fail to predict the future observation, like a cow or a lion or a lion running in front of the car? Yeah, you make a good point as well, and that's kind of like the issue of exponential rarity, right? You're needing to stack the actual actions on top of each other. So yes, the model might only include the car, or sorry, the future would only include the car, and but the model might fail to predict the actual action that occurs. Yep. And again, a lot of that has to do with the fact of you're combining, it's not quite a three body problem, but it's a little bit similar to that in the sense that you're trying to combine the prediction of rare events. All right. So basically, we have tons and tons and tons of video, and to an extent, without the proper curation tools, it's like trying to find a needle in a haystack. So there's basically three ways to work with large video data. The like naive approach is you like download everything locally, it's petabytes of data. That doesn't scale very well. There's cloud native querying, and you query the data, where it lives, and you just stream what you need. This is actually something that the 51 supports out of the box. So like you can write filter expressions like find me rainy scenes with pedestrians, right? So here it's actually doing like a direct label match here. And you can get back matching samples, but like the source of truth for the data is in some backend object store. Another thing we're going to exploit here, the third approach is embedding based search. So the idea is you compute embedding once. Each either video if you're doing video embeddings, a lot of stuff just for practicality reasons. It's still done with frame embeddings. You match them with a dimensional vector. And then you can do something like similarity search. So you can qualitatively explore the embedding space, which we'll see in a moment. But you can also do something like either sample comparison through uniqueness or similarity, or you can, depending on the model, use natural language as well to search for samples. Um, and the benefit of that is for the latter, labels aren't necessarily needed, right? The embedding captures semantic content directly. So for example, in this code here, this is showing how in 51 you would load the data set, and then here we're filtering, by weather, and here we're using labels, filtering by weather and label, and then you launch the app and explore. And I'll pull up a Jupyter notebook in just a few minutes that explores that. But the idea is that, think of 51 is sort of like a visual, almost like a VS Code, an IDE for managing your data sets from the annotation, training, curation, training, validation pipeline. Okay, so once you have embeddings, if needed, you can project them down to 2D with tools like UMap. And then what you basically get is a navigable map of your entire data set. So similar content will cluster together. You can color code by different attributes or metadata. So on the left, you can see what's basically thousands of points. You can see the cluster structure. You don't need to watch a video to get a sense of the organization. You don't need to look at individual samples at this point. On the right is interesting. This is using an example from a paper that colleagues at Voxel 51 wrote on what's called zero-shot core set selection. So basically, this is an algorithmic method of finding underrepresented reasons and then mining those reasons. So there's both qualitative and quantitative metrics. So again, the embedding space, you can very qualitatively get a sense of, okay, what might be underrepresented through visual inspection. And then through core set selection, you get an algorithmic quantitative approach of finding unique samples that might represent rare categories that then might also represent failure categories. All right, so let's actually do an example of what this looks like. And I'm actually going to do this real quick. I have the QR code at the end, but bear with me one moment here. I'm actually going to share the repository directly in chat for those that might be interested. I'll have the Jupyter notebook here as well. I want to be a little bit hacky here and directly in Zoom chat share the repository, and then there'll be a QR code and a link to it at the end as well. So here I have a Jupyter notebook up, and I'm going to open this notebook. And here is what we are going to do. So ultimately, what I'm going to work with is, again, this is meant to be reproducible locally. So the scale of the video data set isn't going to be huge, but this is meant to be representative. So I'm going to use a data set that's in what's called 51's data set zoo. It's called Quick Start Video. It is a subset of the Berkeley Deep Drive data set. So the first thing that I'm going to do is so this first example is going to focus on embeddings plus similarities computation and similarity search. Today's natural language models for this sort of thing still work best with frame embeddings. Oh, I'm sorry, I didn't send it to everyone. I sent it to only hosts and panelists. Give me one second. There we go. Should be now to everyone in Zoom chat. Sorry about that. Okay. So for this example, we're going to convert our videos to frames. So just to give you a sense of where we'll start off here. Actually, I'll start with directly the Python calls because this is how you would do it, and I'll open up the app shortly. So this is a Python library. I've imported the 51 libraries. I've imported what's called the 51 zoo library. I've also imported some other processing tools. And what I'm doing is I'm loading this quick start data set, which just downloads several videos that are a subset of the Berkeley Deep Drive data set. Give me one second here. And this should output here in just a moment. Dataset already downloaded. All right, so here I've downloaded the dataset. Here are the different sample fields in the data set. I've also extracted frames. So again, nothing too crazy. There's 44 frames total. Again, this is kind of a small naive sample starting out. And then in the second place piece, I've computed clip embeddings. So I've loaded the clip model from the 51 model zoo. This is just really an integration to Hugging Face in a lot of ways. Then I've generated embeddings, the embedding space, and computed embeddings for each frame. And what I've also done is I've computed similarity. So I've used a library called 51 Brain that does an algorithmic similarity computation as well. And I've stored it here as a key that I can reference later. All right. Next, what I'm doing for the moment is going to be a little bit naive. Again, this is a small data set. So in production, physics scores are going to come from an actual validation pipeline. Here, I'm going to simulate those physics scores. Again, that's not the kind of climax of this demo. The climax of this demo is going to be more the similarity computation and then mapping that to a subset of the data set. So what is actually currently considered failure cases don't really matter quite yet. Those would be, again, done by a validation pipeline. We'll kind of talk more about that. But for now, we're just going to say, okay, a subset of these samples are being given the skeptical eye by a validation pipeline. So again, somewhat pseudo-randomly, zoom out a little bit, we're going to say that 6 of our samples have some kind of physics violation. And then the last thing I'm going to do here is I'm going to compute the 2D visualization of our embeddings so I can then color code the sections that might be considered like our failure samples. Right. So it's going to compute and generate the visualization. That'll take just a moment. All right. That should, oh, sorry, not quite done yet. Okay. So again, at first, I'm going to show you kind of two data sets here. This first one is going to look fairly small just for this local run. But what I'm going to do is I have this on the same VM just exposed over port 5151. So give me 1 second here. Oh, sorry, I need to actually launch it. Sorry about that. So I'm going to do session equals fo.launch app dataset. Give me 1 second. It's not going to render properly here in the notebook, but it will render in the browser, or at least it should if the demo gods have favor on me today. Let's try again. Yeah, there we go. Okay, so here's my data set. It's 10 videos broken up into frames. These are largely dash cam videos in this case. And what I've done is I have computed clip embeddings of the data set. So here are the raw embeddings. Again, small cluster here, but I can color by the physics score. Again, this is pseudo-randomly generated, but that's not quite the point so far. So for example, if I were to, cluster low scores, that would isolate the videos that, sorry, actually I need to re-lasso this. That would isolate the videos that like it thinks aren't matching physical reality. Maybe there's like weird shadows. Maybe the movement based on timestamps doesn't look correct. Again, we're assuming this went through a physical validation pipeline, and I'm kind of hand waving that away for the moment. Where I do, and then you can like, look through individual samples and so forth. What I do want to zero in on is specifically this piece, semantic search, where you can query by natural language. So the idea here is based off my, based off my space, I've computed similarity embeddings. What I could do is I could do something like a natural language query, for example, say a busy intersection with pedestrians and cars, and very easily construct a view of those results. And then later I could map that view. I can isolate that view with respect to what I consider to be my failure cases. So for example, if there are rare scenarios that I know I want to make sure my model performs well on, I can direct that towards the cases that are currently deemed to be in like physical violation. So if I then, that's correct. Yeah, so if I've created this view, failure queue, 12 samples need review. Oh, I'm sorry, this skipped down. Okay, so I've done the view of similarity search. Let me go back here and I refresh my page. Yes. So these are the samples. Let me get rid of this for a moment. That is deemed to be based off that search. And again, this is a small sample set, but this is what based the similarity search calls busy intersection. Just purely based off this video sample, the intersections don't look all that busy, right? There's a car or two, there's a crosswalk, there's some people, so that's probably what it deems here. But where the scale will matter is when you're working with very large data sets. So, it's just a quick aside. If you're working with very large data sets, it's very unlikely that all of your data will be, or even all the metadata will all be stored locally necessarily. And you would therefore, it would be therefore impractical to, generate embeddings on like terabytes or petabytes of frames. That can be difficult to manage depending on the level of infrastructure you're working with. So 51 has an integration with data lakes through a feature called data lens. So let me open up a larger subset of the Berkeley Deep Drive data set, which I have here. There's some more labels on these, so I'll kind of get rid of these for a moment. And if you want to mine for failure cases, but the data is still in your data lake, it hasn't all been imported to 51. If you're using a data lake like Databricks that has uh, like vector search integration, you can use the data lens feature to connect to your data that isn't yet in 51 through just API integration with your data lake. In this case, if my data source is Databricks, I've enabled contextual search, and then the same thing that I searched for here, say a busy intersection with pedestrians and cars, instead of leveraging like a directly computed embedding space here in 51, it's using vector search in Databricks to largely do the same thing. It's doing natural language search. It's functionally doing a similar similarity search. But now we can choose to augment our data set with samples that are in our data lake that might not yet be in 51 yet. So then I can choose to select some of these samples. And again, so quick note, the fact that there's labels on this is this happens to be using labeled data in a data set, but it actually doesn't strictly matter here. If it didn't have like object detections on this, that wouldn't really affect the result of the search because it's using the embeddings is not computed from labeled data in this case. So then I could choose to import the data and then augment my data set with it. Right, give me one moment here. All right. And then lastly, just to tie this home, sorry, let me make sure I'm in the right place here, is I can I queried by description. And then lastly, the last step is to isolate just the failure. So I have my view of results similar to a description within a certain confidence threshold. And then I can say, only show the failures from that search. So if I go back here, I think it'll be a very, very little data in this example. Oh, I'm sorry. No, this is just isolating failures in general. So these are isolating a physics score of less than 0.5. Let me see here. Yeah, and this would also act as a review queue. All right. Okay. So this first demo was really all about finding the data. So curation is critically important because the idea is we want to be able to curate a data set that we can actually like work with at meaningful scale while also working with subsets of the data that most need our attention. So let's look at these two columns here. On the left, this shows what existing appearance metrics tend to actually check, right? Things like texture quality, color distribution, semantic layout. Basically, it's more like, does this look real? On the right, we actually need to represent physical reality. So for example, do objects persist correctly across frames, or do they, vanish and then reappear? It says my shared screen is cut off. Can you zoom out? Is anyone seeing the same where my shared screen looks cut off? Let me see. I can try. It looks like it should be fully sharing. Let me know if anyone else is having issues. Okay. That worked. Okay. Someone said that worked. Better now? I'll try one more time. Okay. I think this is uh, an instance of the um, presentation software I'm using. It can be a little wonky sometimes. Let me know if you still see issues. I'll keep an eye on it. Okay. Let me adjust one more thing. All right, so object permanence. Does gravity work, right? Like, are unsupported objects actually falling? When you say like turn left, does the car actually turn left? Are objects tracked consistently? Like these are answering fundamentally different questions. That is it matching physical reality? So um, there's a real gap between video generation models and like explicit 3D scene generation models, right? Video generation is not caught up yet. Um, because right now they're very focused on physical realism, not physics understanding, which we talked about before. So how do we actually detect these physical outcomes? So there's really four strategies that we found work pretty well. And the good news is all these can be implemented with off-the-shelf models. So the first is object tracking. That is, run a tracker on generated video and our detections matching across frames. Um, so you'll run a tracker like SAM2 or segment anything model 2. And then you'll check to see whether like the IDs are persisting across frames. Like if an object is there in frame 10 and then it leaves and then it comes back, right? You're violating the conservation of mass, right? So that's a very common failure category that's caught. Depth estimation is another one. So if a car that was behind a truck suddenly appeared in front without passing it, that's a hallucination. There's collision geometry. So like we're looking for like physically impossible overlaps, right? Two objects can't occupy the exact same space at the exact same time. And then things like motion magnitude. So we can check to see whether velocities exceed reasonable physical limits. So for example, if a car moves 200 meters between two frames and that doesn't match the time series, that's gonna, again, violate what we would expect out of these scenes. Um, so stitching these sorts of things together are what can give us a physics validation pipeline. But one of the most important things that teams also don't measure, and they need to, is temporal drift. So when you're generating video with a world model, it's very often, and I think this was mentioned before maybe in a comment, that the first few frames can be fine. The model starts very grounded in reality, but like as you generate further into the future, there's an exponential accumulation of errors. Like any inconsistencies at first, even if they're very small, they cascade, and the errors compound, and then like the model just starts rapidly hallucinating. So, for example, again, this is kind of an illustrative chart here. If the physics validation score starts near 1.0, it'll follow what's often, it's not always this way, but often follows what's like an exponential decay, right? And then the red zone here and kind of over here is where the model really starts losing grounding and predictions are no longer useful for downstream predictions or model training. So we're calling this the drift horizon, right? It's something every team needs to learn about their specific model. At what point is it no longer useful? And then there's some published data that backs this up. So uh, Henschel et al. In a paper published in CVPR last year found that most commercial diffusion models manage about 5 seconds of consistent generation before errors start to compound. Genie 2 is currently the leader, but there's certainly not infinite horizon consistency. is it claims to be consistent up to 1 minute. Um, but the thing is that especially when you're doing like AV simulation, you often need like a decent amount of time to evaluate a full driving scenario, like at least 30 seconds, often more. And that can be the silent killer of world models. Like everything looks fine until 5 or 10 seconds. And then, 30 seconds in, cars are driving through buildings and so on. All right. So let's finally put all of this together into a concrete pipeline. What would this look like? So we can kind of conceptualize it in 5 stages. Generate video with your world model, detect objects with a tracker, check the physics constraints on each frame, score every frame, and then curate the failures for human review. So this is kind of part of a skeleton, right? We kind of this is again a skeleton, right? It's assuming a couple functions that like aren't defined in this screenshot. But the idea here is we import 51, we load our labels and data set. For each sample, we run validation. Um, we then find, like we do what we did in the last example, which is finding low scoring samples, and then um, identifying them and curating them in the app, and then, using those as our basis to move forward. So we're going to do another demo here in just a couple of minutes. But to just make this really concrete, um, there was a paper that modeled 14 frontier video generation models across 350 prompts, 67,000 human annotations. And the five most common violations are all in this table. So violations of Newton's laws, conservation, so like objects appearing, disappearing, occupying the same space. Penetration, right? A car just passing through a wall or a vehicle. Gravity, unsupported objects floating in the air. And then fluid dynamics, violations of that were like water's flowing uphill or it's freezing in ways that don't make sense. Um, a really interesting finding. So here's also something it found is that image to video models consistently score lower on physics than text to video. Um, and that kind of makes sense, right? Because image to video is forced to maintain a continuous image, like visual state, right? And that can be harder to get right than from a text description where the model might have some more freedom. Um, so what we're going to do now is we're going to move into a second demo, and it's going to be a slightly different type of validation. It's going to be automated temporal auditing with a vision language model. So let's show you what this looks like. This demo is going to take a slightly different approach. Instead of doing kind of like manual physics heuristics, we're going to see what it's like to use a state-of-the-art vision language model as an automated auditor. So just before I jump to that, the approach is going to be like what kind of asking the model, what do you see? When does it appear? And then compare the answers to ground truth. And again, part of the goal here is to um, kind of automate, kind of begin the comparative curation automated process in a way that can save us time later with more manual approaches. So I'm going to click out of demo one. I'm going to open demo two. And here's what we're going to start with. So similar to before, I'm going to load the same dash cam clips as the first demo. And it so happens that, Berkeley Deep Drive already has ground truth annotations on them. So it has some frame level bounding box annotations already, person, vehicle, road sign. That's in the original data set. But what I'm going to do here is I'm going to convert these per frame bounding boxes into temporal events for comparison. So for example, like if the person bounding box appears in frames 30 to 50 or 90, like that'll become like, oh, there's a person there, temporal event against those frames. So like there's some real ground truth here from those annotations. I'm not, nothing's fabricated here. Okay. The next thing that I'm going to do is I'm going to load a vision language model. So I'm going to load the Qwen 3 vision language model, just because it's pretty easy to run locally. So it requires about 4 gigs on the GPU. Um, and so I'm going to load that. And again, this is just going to use 51's native torch integration. And again, this is just a Python script here. We'll wait for this to load for a moment. So this is just pulling from Hugging Face. Okay, so this next step, just I'll hover on this for a moment because there's a lot going on here. I'm going to extract 8 evenly spaced frames from each video. I'm going to show them to the model. I'm going to have the model then tell me what's visible and when, and it's going to use the same vocabulary as the ground truth labels. But the model's never seen the ground truth annotation. So it's like it's running independently, but I'm just aligning the label names accordingly. All right. So it's ready. And now this will take a minute or so. Don't worry about that warning here. That's not super relevant to us. It's going to run on each video. All right. While that's running, I want to give a shout out to a colleague of mine who has worked very heavily on um, working with, give me one second here, vision language models and integrating them with Voxel 51. So it's my colleague, Harpreet. He has an excellent Medium page where he's all about taking kind of the state-of-the-art data sets, models, and natively integrating them with 51. Part of the reason why it's fairly easy to cleanly do this without an incredible amount of Python code is because Harpreet is able to natively kind of include these integrations in our data set and model zoos, and he builds plugin and integrations that make it pretty straightforward. So shout out to him. This is about 60% of the way done. We're getting there. Is a preview of what we're then going to do next is then going to calculate temporal intersection over union. So this is going to give us, based off the VLM's findings, true positives, false negatives, false positives. And again, the goal here is we are taking a skeptical eye both towards our vision language model and our ground truth, and are trying to find places in which they disagree. It could be that the vision language model is just not good enough. It's missing easy things, tons of false negatives. It's hallucinating, tons of false positives. But it could also be there's gaps in our ground truth as well. And that's extremely uh, critical because false negatives at the ground truth level, missing data can like poison everything downstream. All right, almost done. Just one left. All right, it's done. So now that just stores them. That just aligns the label names, so we're good there. This evaluates the detections. Okay, so not awesome, right? Again, local model, small data set, 13 true positives, 17 false positives, 13 false negatives. This gives us something to go off of. Again, we'd probably want to fine tune and improve the model we're used here, or maybe like use a better one. But the goal here is to really find disagreement. So a couple things we can note here. First of all, should I open the app yet? Oh yeah, sorry. And we're also going to find disagreements. It's where does the VLM disagree with the ground truth? So we are going to, yes. So ultimately, um, we want to find samples with false negatives, samples where the VLM missed events, and then also samples with hallucinated events. And there's a couple interesting cases here. So now, if I open up the app, so I'm going to reload here. Oops, sorry. Let me do this. I need to actually launch it again. Give me 1 second. Where are my labels? Hold on 1 second. Right here. Okay, sorry. I just need to go back to the quick start video. So these are the samples in which the model disagrees. And what we've done is we've added tracking labels, and they show where in the clip the VLM is deviating from the ground truth. And again, sometimes it's hallucination, sometimes it's just like not finding things. And again, there's a couple examples here that are kind of silly. It's like something about the VLM, let me get rid of this, is saying, okay, the ground truth is properly detecting all of these. And for whatever reason, Quen's like, I don't see a car. So again, that's something we would need to look into. But there are a couple interesting cases where, for example, if I open up this scene, Quen is hallucinating a road sign, which I'm willing to bet is this like basketball hoop, right? So like I would not be surprised if a model's like, yeah, that's like a road sign or a stop sign or something like that. So this would be something plausible where we need to be like, okay, there's a basketball hoop in the street. How might our model like freak out or hallucinate because of it? So, so far, we're just taking the full clips where there are instances in which the model and the ground truth disagree. But we can also isolate it even further. We can do kind of the equivalent or sort of equivalent to what's called patch embeddings. So if you've worked with 51 before, you might be familiar with the concept of patch embeddings, which or patch views, which says that, instead of like the full sample with all of the different objects on it, we're instead creating an individual sample for each detection, right? So, and then we can compute embeddings off of that. And therefore we can say, okay, it allows us to map samples and detections one to one. We can do something similar here where we can say, um, we're going to isolate the reviewable clips from the disagreement regions. So we're going to take only the portions of the clips in which there's the places in which the model and the ground truth disagree. So what this will show here, did I reload 50, reload 51? Yes, yeah, session view is now the clips view. And what it actually did is it filtered to places that the vision language model might be hallucinating. And again, the goal here is to not, treat the vision language model as inherently correct or incorrect. The goal here is auditing, right? It's to say, okay, it thinks it's seeing something that is not in the ground truth, but is the ground truth wrong or is the vision language model wrong? So here's actually a really good example, right? Like, is this right? I'm willing to bet that the vision language model thinks this is a road sign, but it's not, it's a billboard. So similar idea. And again, all this is doing it, and notice as well that these are spliced from the same clips, right? So we have one sample per kind of metadata attribute here of disagreement. So portions in which it is relative to the ground truth hallucinating a vehicle being visible, a road sign. So here's another interesting case, right? Here there's actually a vehicle, but for some reason, so this is where we need to do more auditing, right? Like why did this not show up in our like ground truth temporal label? Oh, was there a road sign? Callum, let's check. You might be right. Oh yeah, look at that. Oh, sorry. Okay, yeah. So part of this might be, let me go back. Road sign visible. Oh, you're right. Okay, you're right. Good point. All right. But again, this is the sort of auditing you can do, right? And you could say, okay, now like, did our temporal mapping of object detections to ground truth? Did we have problems in that, right? Because it looks like, downstream, we're seeing that it appeared to hallucinate a road sign, but ultimately it was captured in the original detection. So again, that's where the auditing can come in. All right. So this, I can't emphasize enough the importance of curation out of all of this. I mentioned before that paper that mentions the curse of rarity. And again, rare cases are rare for a reason, right? In like real world driving, for example, crash frequency is about 1 in a million miles. So the problem in real world models is that the scenarios that matter, like near misses, especially unusual interactions, like those are the rarest things in our data set. Um, but those are the ones where we need to get the physics right uh, the most. Oh, cut off again. Ah, let me know how that looks. I'm trying to get it reset. Let me know if it's still cut off or not. Sorry about that. Good. Okay. Yeah, something with the um, presentation software. So random sampling is not going to surface the rarest scenarios. You need targeted curation. So there's a couple approaches to these. Number one is pattern mining. That is, you're saying you're looking for a causal, here's an action, and then here's a consequence, right? And you're looking for temporal co-concurrence of those. You're saying, okay, where is there an action and then something that happens close together? That is like, is there like a hard break and then a near miss, for example, within just a couple seconds of each other? And that's data worth extracting. Um, what you can do is you can also cluster embedding similarity with the logical combination of known causal pairs. So, when we curated the embeddings, we did like natural language search of like pedestrians in an intersection, right? If you're using a natural language approach like that, you can start to combine kind of phrases and semantics to try and find these sorts of pairs. Um, and then, if you've identified like 10, hey, here are the most common near miss scenarios, you can query your embeddings for those. The second approach, sorry, one second here. Yeah, sorry. The second approach is literally just like writing in code, right? Um, but this assumes you have labels for that. So there's a little bit of a chicken and an egg problem. Okay. Lastly, once you find these causal scenarios, you need to annotate them with kind of a real structure. So like what action initiated the chain of events? Um, what was the affected object? What was the temporal span? You also need to pay attention to the counterfactual. So, like, if the action didn't happen, what would have happened without that trigger, right? Without the break, there would have been a collision. Um, so, in 51 supports annotation uh, as of this year. So, for example, if you do need to make a frame change, right? So, like, again, let's think here. Let's do the example where it's like, yeah, hallucinating a person visible. These are false. These are hallucinations. But if you need to change annotations, if something was wrong, there is an annotate tab here in which, sorry, I think, oh man, I didn't turn on annotation here. Okay, let me go back to a different data set super fast just to show you the annotate tab. Again, it's about what you expect, right? You can create a schema like detections, for example, add classes, right? So here are my bounding boxes. And then from there, I wanted, do I have my detections? There we go. Nope. Saved it. Try just making sure it's visible. Make sure this is correct. There we go. I don't know why this isn't showing up. Oh yeah, sorry, I have to draw the label. Right, that might be a car, for example. So again, and then you can change existing annotations, right? So if I like have an existing annotation that's in my schema, right? I can edit it if needed. I can delete it. I can change the label. So again, there's manual curation you can do here as well. Quick note, I won't spend too much time on this. Quick note about fine tuning. Um, Basically, it pays off in the long term. Um, so the pattern across all these paper, without like totally diving into things, is the right data matters than more data. So like with the right conditioning, the right training objective, targeted curation is the highest leverage investment. And basically fine tuning your data and then training the model downstream from that fine tuned data is has a really good payoff. Um, So for example, NVIDIA Cosmos, when they added action condition training data to their post-training pipeline, I think pose estimation went up from 4.4% to 62.6%, right? That's a 14-fold improvement. All right. And then the last piece, this is kind of where more of some of the human element comes in, is red teaming. So the way it works is something like this. You'll deliberately design scenarios that are meant to break the model, generate output from the world model, have the team review the results, and then, tag category failures, and then those tagged failures will be retrained. So what you need scenario designers who craft those adversarial inputs. So like, what if two cars reach an intersection at the same time, or a ball rolls into the street? Um, and then you have domain reviewers that look at videos and says that is physically incorrect. You'll have people triage the findings. And the tooling really matters here, but again, it pays off very strongly down the line. So, people will be tagging specific frames and commenting on each other's findings and things like that. Thankfully, 51 supports, at least in the 51 enterprise version, it supports, collaboration and shared data sets and data set versioning where that's possible. But again, the idea here is that we're able to um, kind of take a collaborative approach to basically having, a deliberate, again, adversarial approach to targeted data set improvements. So just real quick, this is often what it'll look like. Again, you have different personas. They take this sort of pipeline approach, and it's very iterative, right? The more we can kind of shorten cycle time on this, the more quickly we'll get improvements. And then some examples here are from World Model Bench's 14 frontier models. So mass conservation, again, the number one failure. Object penetration, again, average failure is 24%. These are the catastrophic ones too. These are the ones that are obvious, physically impossible, deadly, right? If you get your assumptions wrong, or if the car model gets its assumptions wrong. And then again, gravity, Newton's laws, fluid dynamics, they're represented as well. So these become your kind of what you're testing against. And every time you update the model, you're testing against these and tracking the failure rates. So let's wrap up and summarize. Key findings. Some of these classic metrics aren't enough. You need physics-aware validation. Looking right isn't enough. In addition to that, you want to take advantage of both qualitative and quantitative approaches to these things. So embeddings, where you can visually inspect the embedding space, direct querying of data, filtering using algorithmic techniques like core set selection. In addition to that, drift can kill you slowly. What does that mean? So you need to measure your validation scores against the full generation horizon, right? Because again, there's an exponential decay of accuracy over time. Rare events are the highest leverage, so seek those out, do scenario mining, do natural language search, um, uh, incorporate vision language models that do zero-shot detection to see where do they disagree with your ground truth and what might that cause a model failure mode. And then finally, keep the humans in the loop through, again, collaborative red teaming, especially like domain expertise is important, folks, right? Like when it comes to like the AV, the AV space, for example, like we have an intuitive sense of a lot of these scenes. That's not the case in every domain, especially in like manufacturing, healthcare. So you need to keep experts in the loop to actually identify if something is wrong, even if the model doesn't necessarily think so. All right. So with that being said, we are at the top of the hour. Any questions other than what was already asked? Quick note, 51 docs are linked here. There's some really good getting started guides based on your industry. There's an install guide. It's just pip install 51. That's really, really easy to do. And then the slides and resources are here as well. One thing that I did note is again, in the notebook, it does presume that I think it presumes that you've run pip install 51. Again, it's just a Python package. So again, take a look in the docs for how to install it. It's quite straightforward, but again, the repo is linked here also. Couple things to follow up on. The first is, again, you'll have access to these resources. You'll receive a follow-up email that contains these resources, the slides. The recording will be posted as well. The event page will be updated with the recording and it'll link to that. So this will all be there. The second thing is I want to give an additional shout out here at the bookend to tomorrow's MCP and skills meetup. You saw the Jupyter notebooks that I was running. This is the sort of thing where, again, the world is awash in agentic coding, but the idea here is let's use it for the things that make sense, like the brute computation analysis, basically, things where I was like just directly running blocks of code in the SDK, right? Right. That's where like contextual skills can really help and integration with the right tools that can just make your job a lot easier and faster. Adonai, my colleague, I can't hype him up enough. He's a whiz at this sort of thing. He'll walk through a really kind of, he and our other speakers will walk through a really cool talk tomorrow if you get a chance. All right. Yeah. Any other final questions before we wrap up? Cool. Good question. Sorry. Why is it named 51? Um, there's kind of a wink and a nod to that. The story is that it's really difficult to find things in your data. So it's an allusion to kind of the mystery of things like Area 51, right? Where it's like, is it there? Is it not there? I don't know what's there. That's what it kind of alludes to, but it's kind of taken on the name 51 has kind of taken on a life of its own since the original naming. But good question. All right, folks, thanks again for your attention. Enjoy the rest of your Wednesday, and I hope to see you online in our Discord. We have a Discord, by the way, in future talks. Yeah, enjoy the rest of your week.